session on template attacks on PQC. We have 3 talks in this session, and the first talk is adaptive template attack on the Kyber binomial sampler, and the speaker is Eric Peng. Eric, the floor is yours.
Right. Thank you everyone for coming to this talk. And today here I'm going to present my work on adaptive template attack on Kyber's binomial sampler. So today I'm going to answer 2 questions. First of all, I want to answer, does the binomial sampler in Kyber present a side-channel risk? Or more specifically, can we perform a single trace attack on the binomial sampler in Kyber? And the second question I'm trying to answer today is, well, if there exists a single trace attack, how practical is such an attack? Can we port it across different devices in a more practical sense? So first thing first, let me explain why I'm interested in this Crystals Kyber. The reason I'm interested in Crystals Kyber is because it's been selected by NIST as the standard for key establishment. And because it bases security on the module learning with arrow problem, it has now been renamed module lattice-based key encapsulation mechanism in this FIPS 203 document. But throughout this talk, I'm still going to call it Kyber because I'm a fan of Star Wars. Right. So this is how the Kyber CAM protocol looks, and it consists of 3 operations: the key generation, the encapsulation, and the decapsulation. And these 3 operations build on top of a public key encryption scheme, which looks something like this. And in this Kyber public key encryption scheme, if we remove the publicly known information, that is the public key and the ciphertext, all that's left are the values that should be kept secret from the outside world. And of all these secrets, if we removed the message, all that's left, all the secrets that's left are generated by this centered binomial sampler, including the secret key, the random nonce, and all the other noise polynomials. So that is why I'm interested in this centered binomial sampler. First of all, it's generate all the secret noise polynomial in Kyber, and second of all, we can find it in all the operation in Kyber CAM protocol, including the keygen, the encaps, and decaps. So the bottom figure here shows how this centered binomial sampler work. So it first takes in a random seed as input and use shake 256 to expand it into some random bit stream. And then the actual sampling procedure takes 2 values, x and y, and then subtract their Hamming weight to get the binomially distributed coefficient s as their secret polynomial output. And there's this parameter eta in the centered binomial sampler that control the bit length of the variable x and y. And in Kyber 768 and Kyber 1024, this eta parameter is set to 2. As a result, the output S has a range between -2 to +2. And for Kyber 512, this eta parameter is slightly larger, and as a result, we have a slightly larger output of -3 to +3. But in this talk, I'm going to focus on this Kyber 768. So from a side-channel perspective, attacking this binomial sampler seems quite simple, as the secret coefficient only have 5 possible values. So a profiling attacker could probably easily attack this target. And alternatively, attacker might also want to target this intermediate value x and y. And since from previous research, we know that a lot of the microcontrollers leaks the Hamming weight information of intermediate values, this may also be very useful. However, the challenge lies with the fact that there are 768 coefficients in the secret key of Kyber 768. As a result, we required a nearly 100% accuracy to extract the full secret key. And oftentimes, this comes with a single trace restriction, as we usually only generate the secret polynomial once. And the table on the right here shows the accuracy requirement. So for example, if we want to have a single trace success rate to reach 90%, we need a template accuracy to reach 99.98%. And to clarify here, when I say success rate in this talk, I mean a full successful attack that extracts the full secret key that includes 768 coefficients. And when I talk about the accuracy, it means the rate of correctly identify one coefficient. So, yeah. So now let's enter the talk about the side channel part. So this is our power side channel measurement setup, where we target the PQM4 crypto libraries implementation, and I use the STM32F303 as my target device. And in order to fit the long traces of Kyber into our oscilloscope, we use our own oscilloscope that has a 2 GB of memory. Right. So the first thing we did in our side channel analysis is to perform a leakage assessment. We here use the NICV to test the leakage of the intermediate value S, X, and Y that's involved in this sampling procedure. And as we can see in this red frame here that, well, the sampled output S has an extremely large leakage. But we couldn't really find useful leakage for the intermediate value X and Y. And the reason is that the PQM4 implementation and also the reference implementation as well, they both utilizes the 32-bit architecture of a microcontroller, which then they compute 16 2-bit Hamming weights in parallel, as shown in the red frame here. And this design not only make this implementation more efficient, it also reduces the leakage of the intermediate values. However, this leakage assessment is not in vain, as we find a really interesting leakage here, locating way before the sampling procedure, and it is at the end of the shake operation. And upon further investigation, we find that this leakage is actually related to the byte-wise storage of the shake output. And we named this byte-wise variable buff. It is an 8-bit variable. It's going to be useful in our track. Now, just to skip out on a little bit, and we talk about the background. So in order to achieve an extremely high template accuracy, we utilize the help of linear discriminant analysis. So in the LDA-based template attack, we first use the LDA vectors. We first use LDA to find vectors that could maximize the separability between data group. And then we project our profiling data set onto this LDA subspace. And as shown on the graph on the right here, after this LDA projection, traces of different intermediate values will be well separated. And then we can use a multivariate Gaussian model to characterize the distribution of these projected traces. And during the attack phase of LDA-based attack, we again projected the unlabeled traces onto this LDA subspace. And then we use the pre-built Gaussian templates to infer their intermediate value using the maximum likelihood. Now, back to our attack. As it turns out that we couldn't really achieve the required 99.99% accuracy when we tried to perform template attack directly on the variable S, even though we only have 5 possible values. But then we find out that we can actually perform template attack on this buff variable and use it to infer the value of S. The reason being that each 8-bit buff value is sampled into 2 secret coefficients, S1 and S2. And for people who did SOSCA, this is the vector graph that describes this relationship. We'll talk more about it later. And alternatively, we can use a slightly smaller 4-bit fragment of the variable buff to reduce the attack complexity from 256 components to 16 components. And we name this smaller variable beta. So back to how we turn the template result of buff to S. So a 4-bit buff have 16 possible values, and these values can be mapped to the 5 possible value of S. And so after a template attack, we get a probability of these 16 possible values, and if we want to obtain the probability of S given the trace, we simply sum up the template attack result of beta equals 1, 2, 7, and 11, which is this 4, 1 here. And through that, we can turn the probability of beta into probability of S. So given this marginalization method, we here show the result of a single trace attack on 1,000 key gen operation. And the result is shown here, that if we use a template of buff, we can achieve 100% success rate of single trace attack. And with the beta template, we achieved 99.3% success rate. So this gives us a boost in our confidence of our attack. So then we want to try out if we can also apply this attack to a more optimized -03 program. So here's the leakage assessment result. And we can see here that leakage of S here is way less in terms of clock cycle than the leakage of -OS program there. So as a result, we didn't really achieve a high success rate, with our buff template only achieved 28.9% success rate, and all the other templates failed. However, we stop our attack here because we already achieved some sort of a success. But for a more persistent attacker, they can keep on complete this attack by using key enumeration or some latest reduction attack to further improve the attack result. So this concludes our first question, that we show that we can actually perform single trace attack on a real device of the Kyber binomial sampler. So the next question we're interested in is whether or not this attack is practical. As I said earlier, we required a 99.9% of accuracy. Can we do that in a more practical sense, like porting the templates from the actual profiling device to an attack device? So here we try to perform cross-device attack to answer that question. We bought 8 devices from 4 different distributors so that we can have our device with different manufacturing dates to increase the difference in our target device. And we also use the TripWhisper socket board so that we keep our own the whole measurement setup the same, only swap out the devices when measuring different data sets. So, not surprisingly, our first attempt of a cross-device attack failed. And the core reason is because there's a model mismatch, as shown here, that causes an accuracy drop. And from table here, we know that a slight accuracy drop would cause a complete failure of single trace attack. So what's the solution here? Well, common portability techniques include data normalization and multi-device training. So for data normalization, we simply just try to match the means and variance of the attack data set to our model. This is quite efficient, but a bit of a crude approach. The other common portability technique, the multi-device training, one tried to come up with a more generalized model that could apply to different devices. But if there is a unique leakage pattern that's presented in our attack device, then this multi-device training may not be able to catch that. So here, we propose a new approach. We name it the adaptive template attack. This is a 2-step training attack that combines a supervised learning technique and an unsupervised learning technique. And with the supervised learning technique, it's just basically just the same profiling template attack. So we here build templates with labels from profiling devices, such as our LDA-based template profiling. But what's different in our adaptive template attack is that we add an additional template adjustment step in our attack phase, so that we can use some unsupervised learning technique to adjust our templates to better fit our attack trace set. So to be more specific, we here use the expectation maximization algorithm to adjust our multivariate Gaussian templates to better fit the new attack trace set that we get without needing to know the label of our trace set. Here, the expectation maximization algorithm is, we also call it the EM algorithm, so different from the usual EM in side channel analysis. Now, as it turns out that using this EM algorithm, we can turn our template portability problem or our model mismatch problem into a parameter estimation problem for a Gaussian mixture model. So this sounds amazing. If we go Wikipedia this EM algorithm, you'll see this explanation, something like it's an iterative method that estimates the parameters for a Gaussian mixture model from an observed data set. Well, we find this description perfectly match our situation here, where we have some observed data that is our attack trace set, and these trace set has a hidden intermediate values that is unknown to attacker, us. And on the model side, through template profiling, we already have a bunch of Gaussian templates, And by combining all of them, we get a Gaussian mixture. And the problem here is that the parameter set of this Gaussian mixture model does not match our observed data. So we can use the EM algorithm to try to find these parameters. So one difference with our method, with the more common EM algorithm, is that we already know the mixture weight of the Gaussian components. For example, if we're targeting the binomially sampled output S, we already know that the mixture weight has a binomial distribution of a ratio 1 to 4 to 6 to 4 to 1. So we don't rely on the EM algorithm to find this weight. We fix it and only use the EM algorithm to find the parameter of the Gaussian means and covariance. Now, this EM algorithm consists of 3 steps: a initialization phase and the EM process that iterates between the E step and M step, and then there's a termination criteria that exit this EM process. So in our EM-based template adjustment, this initialization phase is the most important part, where we try to place our Gaussian templates as close to the respective cluster as possible to help facilitate our EM algorithm. So we do that by matching the mean and variance of our model to our data set, sort of like data normalization. But here, instead of moving the data, we here move the model to our data. And then we enter the EM process, which consists of the E step and an M step. So starting with E step here, the E step evaluates the responsibility of each Gaussian component to each sample. Essentially, we try to determine how likely one sample comes from the blue one, the green one, the orange one, or the purple one. So and then we assign the probability based on the distance of the data point to the Gaussian components. Or a more intuitive view is that we color these dots based on how far it is from the Gaussian component. And then there's this M step here. So based on the responsibility that we get from the E step, we then update the Gaussian components parameter by recomputing the weighted means and weighted covariance. A more intuitive view is that based on this coloring, we try to move our Gaussian templates to fit this coloring. And the EM process iterates between these 2 steps. So again, with the E step, we recolor these dots based on the Gaussian components there, and then we move the Gaussian components to fit the new coloring. And then again, recoloring and move the Gaussian components. And after 5 iteration, 10 iteration, 20 iteration, and then it finally fits our data quite perfectly. So we then exit our EM algorithm with a termination criteria, and here we set it as a maximum number of iterations as 30. So after this EM adjustment, we expect our templates are now fine-tuned to fit our attack trace set, as shown in the graph here. So now let's show the actual result of our EM adjustment to our templates. Here is the beta templates, that is the 4-bit fragment template. And here in this graph, here we can see that this Gaussian template misses its mark by a lot. And this one sort of misses it by a little. And with the help of our EM adjustment, all our Gaussian templates sort of find its own data clusters. And as a result, we can improve our template accuracy from 56% to 84%. And this EM algorithm also works on a template that has a lot more components. That is the 8-bit buff template, where we have 256 components. And here is the before result. Here's the before picture of our EM adjustment, and here's the after ones. And I want to stress that this graph here, we only show the 3rd and 4th dimension of the LDA space, meaning there are more LDA space that could further separate the dots that seems close together here. And with our EM adjustment, we can improve our template accuracy of this buff template from 48% to 55%. Now, so here is the result of our actual cross-device single trace attack. So on the left table here is our template attack without any portability technique. And in here, we can see that almost all the template portability attack failed in this red cell there. And the diagonal one are the only one that achieves some sort of achieves some sort of success. And most of them come either from the device itself or from the device from the same distributor. And with the help of our adaptive template attack, we can improve our single trace attack success rate from 0 to almost 100 for most of the case. And this adaptive template attack can be applied also alongside other template probability techniques, such as data normalization. So here we can see that using data normalization, we already have a pretty good template portability ability. But with the help of adaptive template attack, we can further improve the result to reach 100%. So yay. And here's the result of a multi-device training portability technique. So here we train on 7 devices. So the only cross-device attack are the anti-diagonal one. And it itself already achieved quite a high success rate in terms of template portability. But our adaptive template attack thrives in this case, where we try to port our template that we profile from the keygen sampler, and we try to use that profiling to attack the binomial sampler in the in-caps operation. So we have a cross-operation attack. And here we can see on the left-hand side here that all the common portability technique kind of fail. Well, data normalization have slight success. But with the help of our adaptive template attack, we can improve all these results to a pretty good success rate up here. So yeah. So to conclude my talk, I answered the first 2 questions I raised at the beginning. That is, does the binomial sampler present a sidechain risk? And our answer is yes. We show that we can perform single trace attack on a real device of this binomial sampler. And how practical is our attack? Well, we show that we can port our templates from one device to another, and we can also port our templates from one operation to another with the help of our adaptive template attack. So yeah, and just a final remark here is that our adaptive template attack is not a replacement for the usual template portability technique. It can be applied alongside other portability technique. So we consider it an additional tool in our SCA arsenal. And hopefully it could help in other cases where people want an extremely high template accuracy. And this concludes my talk. Thank you for your attention.
Thank you for your great talk. If there are any questions, please just come to the microphones in the middle. Yeah.
Hi. Thanks for the talk. It's very practical, very interesting. One thing that I couldn't exactly get was when you were introducing the EM adjustment.
Right.
It sounded like you were manually adjusting the templates. Is that the case?
The only manual part is we try to match the means and variance of our GMM model to our input data set.
Yeah, but then how do you know?
Right, and
how
afterward,
do you know which label is?
Oh yeah, so that is one of the problems. So we don't really know the label. That's why we need to place. So this initialization phase is very important. We need to place the blue model close to this blue data. If we didn't do this initialization, if we start our template model as random, then the blue model would randomly latch on one of the clusters, and it would have a completely wrong result. So this previous this initialization phase utilizing the pre-built model is quite important in our case.
Yeah, but then how do you do it? Is my question.
Just match the means and variance of the GMM model to the data.
Oh, you take a best guess? Or?
Sorry?
Because you're in linear subspaces, right? You have no idea where it should be.
Yeah.
Which label. So you take a best guess and then evaluate, and if the attack is successful, you can do something useful with the...
Yeah. Also, we find that with our LDA projection, these data clusters sort of have a good... well, the relative location doesn't change much.
Okay.
So yeah, so this thing works.
Okay,
if it got messed around, this thing wouldn't work.
Okay, great. Yeah. Thank you.
Maybe one more very quick question.
Yeah, actually a quick question. At the beginning, you mentioned that you were getting most of the leakage because there was a byte-wise transfer of variables between Ketchak and the folding operation. Have you tried to correct it, like to make it so that 32 bits are moved at the same time, and so if you were still getting leakage from it?
Sorry, the second half, have I tried to?
Like, did you try, instead of having like a byte-wise transfer of this data, to move the bulk of data 32-bit by 32-bit?
Oh, I didn't try to modify the implementation. I expect that if this is not stored byte-wise, if it's stored in word-wise, then our attack would probably fail, and we need a lot more effort to do that.
All right, thank you.
Then let's thank the speaker again. And our next talk is OT-PCA, new key recovery plaintext checking Oracle-based side channel attacks on HQC with offline templates. And the talk is given by Chen Gu. Thank you.
Good afternoon. Welcome to my talk. I'm Chen from Lund University. So I will talk about this OT-PCA. You has this paper, and this is joint work with Haiyue. So as we know that HQC has been selected as a NIST post-quantum CAM standard. So it is it is very urgent to understand the implementation security of HQC at the current stage before it is widely deployed in our infrastructure. So we study its implemented security through this side channel attack part. Then we propose a new plain text checking Oracle based attack. So this is a like key recovery attack, and the new part is a method that allow us to extract probabilistic or soft information on hundreds of secret bits simultaneously. So the importance of work lies the importance of this plain text checking Oracle-based attacks. So first, it has high relevance, not only limited to side channel attacks. It has relevance also in key mismatch attacks and also in some fault injection attacks. Also, for this kind of, even you limit it to side channel attacks, it can, you can create this Oracle-based attack from multiple leakage types, for instance, like power, electromagnetic leakages, like timing leakages, cache timing leakages, also even some very complex microarchitecture behaviors. Another thing is this kind of attack can exploit very generic leakage sources. For instance, you can build this. You may build such an Oracle-based attack from this decryption phase, from this re-encryption phase, or this ciphertext checking phase, from this FO transform. So let's see the new results. We actually obtained a significant reduction in the required Oracle cores. For instance, for HQC 128, we achieve a 2.44 reduction with a perfect Oracle, and we achieve a 7.6 fold reduction if the Oracle is kind of inaccurate with accuracy of 95% of accuracy, which is a more practical case. So let's put our research into the general into the context. We see that our community actually has put a lot of effort to try to create more efficient PC Oracle-based attacks on HQC. We see that from the beginning, we need more than 800,000 traces or Oracle cores. Then we reduce it to the previous state of the art, zero tester. We just need about 1,000. For this new research, we further reduce it to 460. And for HQC 192 and HQC 256, you can see the improvement factor are even larger. So the reason is we achieve this improvement because we kind of develop a new method to extract the secret information. So the beginning papers from CHES and PQ Crypto, we mainly recover these individual secret bits by multiple attempts because the dimension of HQC, because the dimension of, maybe it's better. Dimension of HQC is so long, so that's why we need such a large number of oracle cores. Then for this SCLDPC, we have improved the method. We try to determine parity check equations using low density parity check codes, and then we use iterative decoding to do full key recovery. So this is more efficient, but you still need multiple attempts to get one single parity check equation. Then we found this zero tester. It's kind of, we need to determine these all zero blocks, but this method actually suffers from this inaccurate oracles. So in this work, we obtain soft information for an entire block, and also it has high efficiency and also very robust to noise in the oracle. So I will organize my talk in the following way. So first I will present some background information on HQC, then I will present the new OTPC method, I will present experimental validation, finally I will conclude the work. So for HQC, so secret key looks like this. You have two polynomials, it's very sparse, x and y, then you generate a uniform polynomial h, and you compute s in this way. So this is public key. Then encryption, we want to compute UV, and we need some intermediate polynomial R1, R2, and E. They are all sparse polynomials, and you compute it in this way. So for decryption, the decoder receives this function after some simple calculation. You find that it's actually the encoding of M plus this small noise term A prime. Because X, R2, R1, Y, and E, they are all sparse, so E prime is sparse. It's like kind of very sparse vector, and the Hamming weight is very small, so most cases, or overwhelming probability, the decryption will succeed. So HQC provide rigorous decryption failure analysis, but in some very rare case, this weight can be large and you got decryption failure. So HQC achieve, like other PQC camps, like Kyber before, HQC achieves NDCC security use CC transform like this Fujisaki Okamoto style. So the cam looks like this. One important thing about HQC is like it uses decoder of concatenated read-Muller and read-Solomon codes. So the decoding works like this. So you have this message way, this vector way sent to the decoder. Then first we group them into N1 blocks, each with N2 bits. Then we feed each block to a read-Muller decoder and got the corresponding result. So you see that we apply read-Muller decoder for N1 times. Then we feed the concatenated result and feed it to one read-Solomon decoder and got the final decoding results. So what is PC oracle? Plain text checking oracle. For HQC, it's roughly this decryption failure oracle. It tells you if the decryption success or failure. As I said before, that it can be constructed from side channel, various side channel leakages like power timing, EM, and complex microarchitecture behaviors. And it can be constructed from multiple leakage sources. Also, it has high relevance in side channel attacks, key mismatch attacks, and fault injection attacks. So for the threat model, we pick this, our threat model is side channel assistant chosen ciphertext attack, means that we assume that there's a device running this decapulation procedure of the HQC CAM, and this adversary will craft the chosen ciphertext and send this ciphertext to the device and measure the side channel leakages, try to recover the key. So the general idea to recover key for HQC works like this, using PC Oracle works like this. So you see that this decryption outcome depends on this input. You see this Y is secret key, so it's involved. You see that this outcome actually leaks information about the secret key X and Y. So in this sense, we can select M, R1, and R2, and E to craft ciphertext with some specific property. We will show it in next slides. And then we just try to work on this decoding boundaries. We reach decoding boundary and to see if the decoding behavior. So it's very important to reach the decoding boundary. So how to do it for this concatenated structure? So we first inject sufficient errors to push this outer Reed-Solomon decoder to its limit, its error correction limit. Then we just corrupting one single additional Reed-Muller blocks. So if this resulting in a Reed-Muller decoding failure, then it may lead to a decoding failure for the whole concatenated decoder. Otherwise, it may be succeed. So this is a basic setting for our OTPCA. So you see that we can pick R1 and R2 in this format. Then we can see that the input to the decoder is just the encoding plus this is a small noise. This is a noise, not small, but this is just some noise. And this is a part of the secret key. So we can see it's like, okay, we just place the noise, and then we add a small perturbation, because you know that this secret key Y is very sparse. So this perturbation may, if you reach the decoding boundary, then this perturbation may change this decoding output. So this to the power k, you can just think that this is a method to shift this secret key polynomial. This allows you to shift different blocks of secret key to different precisions. So the main idea is like if we just add this perturbation, then we will reach some state, like we may change from success to failure, but we don't know what we added. So the idea is, okay, we just sample. We can sample according to the secret key distribution, and then you just store that, okay, this kind of secret patterns, some pattern lead to failure, some pattern leads to success. Then you just think that, okay, if it leads to failure, then you just do some statistical analysis on that and build some statistical property. We called it offline templates. So then next time in the real attack, when you observe such state, you think that the key should follow this property. So this is a basic idea of this offline template. So this is an example of this offline template. You see that this empirical, so this is a priori probability. So before this, knowing this decoding output, you've seen that each bit, each position are equal, just with probability of this one to be 1. This is quite small, but still each positions are equal. But when you observe this decoding output like success or failure, you can see that some positions are extremely likely to be 0, and some positions are more likely to be 1. So this is just this software information about the key bits, and each time we can get information about 384 bits. Maybe that's not that accurate, but still, this is a lot of software information that we can exploit. So in this way, we introduce this OTPC framework called offline templates for plain text checking attack, or Oracle-based attack. So the idea is just we use this pre-computed OTs. We can obtain software information about hundreds of secret keys for just one single PC Oracle call, and we need to do some maximization to maximize this information gain. The reason is we want to really stand at this decoding boundary, because if you are very far away from the boundary, and every time you got success, then you got no information from this decoding output. You want like half probability to be failure, half probability to be a decoding success. So in this sense, we have this attack flow. So what we do is we have offline phase. So first we optimize E, and we try to build the OTs. And unlike Oracle query, we just get the decoding output, and we apply OTs to compute some reliability scores, and then feed this score to this variant of this information set decoding algorithm. So one thing to note is that this offline phase or this optimization, it's not like templating. We try to profiling a device or profiling a key. We are actually profiling the behavior of HQC decoder. So if HQC still works as the one documented in the specification, then this task you only need to do it once, and you can place it somewhere, and next time you can use it to attack any implementations and any keys. So let's see how the offline phase work. We want to optimize a set of error patterns to solve two optimization problems. The first problem is we want to maximize the binary entropy of the decryption outcome. It just means that we want half output to be success and half output to be failure. So we have a genetic style algorithm by just iterative bit flipping and reach this best state. The next part, we also want to maximize the pattern distance. The reason is like we have multiple observations, like these T observations, so we just want each observation to be independent. Then we have the maximized mutual information. So what we do is we just maximize the sum of pairs Hamming distance. We implement this optimization, but actually found that actually this is not that necessary because it has a minor effect in the performance. I think the reason is because the pattern is of size 384, so it's a rather large dimension. So any random patterns, they look very different. So this is step to build OTs. We just simulate sparse vectors, just generate a lot of low-weight vectors following this secret key distribution. Then we just feed each vector and feed this to this public available decoding function. And we record results. Then we aggregate these vectors to see, okay, this group belongs to the success, this group belongs to the failure, and then we estimate the probability for each bit. So in the online phase, what we do is first we place this E like this, you see. We control the first block, and then the remaining 45, because N1 is 46 for HQC 128. We control the first block. For the remaining 45 block, we just set 15 O0 block, and the remaining are all 0 blocks. So it means that only this block is sensitive. So we need to shift, by varying key, to shift other blocks to the first block, so we can get information of H blocks in X and Y. Then we construct ciphertext like this, and then we just feed it and query this PC Oracle with each one to get this decryption outcomes. Then we just check according to the decryption outcomes to look at this offline templates and get this conditional probability for each test. Because we have T patterns, then we just multiply them. This is like a reliability score. So we feed this to a modified ISD algorithm for full key recovery. So this follows this thing size Sandriel framework. So we just kind of write it into this quasi-standard format. But note that in traditional ISD, we will sample this multiple times. Here we just have a one-pass ISD. So we just do this Gauss simulation according to this reliability scores. So we can put this the positions most likely to be 1 at the beginning, most likely to be 0 at the beginning. So we think that the first T0 positions are most likely to be error-free. So we just sample T1 positions, assume that they are error-free. This will make this polynomial smaller. This pressure check matrix smaller. And then we do a collision approach like the Stern, so we just find low weight error vectors by colliding two lists of elements with small Hamming weight. Here we pick it to be 2 or 3. If it is 2, it is much smaller than a Gaussian elimination at the cost of this collision procedure. If it is 3, then it's comparable to Gaussian elimination. So you can see the simulation results. We show the distribution of the number of errors in the first n positions of the reordered vector. You can assume that without, in the random case, you should have 66 ones in the first part. But actually, if you have 5, then on average, you just, the mean is like slightly larger than 4 if you have 5, t equal to 5. Then here rho is like the oracle accuracy. So we can see that this is a success rate. If you choose t as to be 5, then you have very okay success probability. So this is very robust to noise. So if even the oracle accuracy drops to 90%, then you just increase 2 from 5 to 11, you still get quite okay comparable success rate. So we need this number of oracle cores because 2 is because we need to target x and y twice separately. So there's 2 and the t times n1. n1 is 46. So we validate this results through this experimental setup. So we use Chip Whisper platform. We target the ARM Cortex M4 microcontroller running this PQ clean implementation. So the leakage source, you know, it's known that actually we can build PC Oracle from multiple leakage sources like this decoding, like this encoding in this rate encryption, also this PRG in the re-encryption. Here we choose this encoding part of this re-encryption. So we pick T27 here. We just want to verify that actually simulation meets the experimental validation very well. So we pick T to be 7. You see that we use a CN classifier, get a perfect PC Oracle with just one trace. So you see that the theory meets the experiments very well. We run 120 key pairs. So let's summarize the contribution. So we propose a new attack. This attack significantly reduced the number of required oracle cores, and we achieve 2.44 compared with previous best. And we introduce a new method that could extract the soft information by these pre-computing templates. And this enabling gaining information on hundreds of secret bits with just a single oracle core. And also this method is highly resistant to inaccuracy in the PC oracles. Thank you very much. I'm happy to answer questions.
Thank you very much for the very interesting talk. We have time for 1 or 2 questions. Okay, then maybe let me start. Have you tried further decreasing the accuracy, or the oracle accuracy that you get? So I think you stopped at 90%. What happens if you go even lower? Do you know that? We
didn't actually,
Okay.
but an easier solution is you can use this. I mean, in attack, you still have this soft information from this oracle, and you can do something, a statistical method to increase this oracle to 90%.
Yeah, thank you.
It's just the gain actually becomes minor and minor when you reduce oracle.
Yeah, it should increase by a lot. Yeah, thank you. I think there's one more question.
Hi. You mentioned that you're recovering the full X and Y, so the full private key of HQC. But for decryption, Y is sufficient. So you could probably save some extraction effort Because if you don't want to have the actual generated private key, just Y is the one you use in decryption. Is there a reason why you would recover the entire thing?
Yeah, it's just so we have this equation,
Yes.
and if you, I think previous method, if you look at this, this 1, 2, 3, 4, this 4 works. We just look at one part. You see that yeah, without so there's information leak lower bound. If you just look at one part, this is I think you need about like maybe 13,000 or 14,000. You just compute this Shannon's entropy. You can see that this is lower bound, but actually if you take x, y part and use this equation, then you can drop it, and kind of this is like computational problem, not information theoretical problem.
Exactly. Okay, thanks.
Then let's thank the speaker again. And our next talk is Full Key Recovery Cubic Time Template Attack on Classic Mac-Leese Decapsulation. And the talk is given by Julius Hermelink. Please go ahead.
All right. Thank you for the introduction. So, hello everyone. I am Nicolas Vallet, and I will introduce you to new full key recovery cubic time template attack on the classic Mac-Leese decapsulation algorithm that I designed with my colleagues Vlad Florin-Dregoy, Brice Colombier, Pierre-Louis Quérel, and Vincent Grosso. So let's start with some context. Classic Mac-Leese is a key encapsulation mechanism that was a code-based key encapsulation mechanism that was among the finalists during the 4th round of the NIST post-quantum standardization process. And it is currently still under consideration at ISO. And my research question was how secure is classic Mac-Leese against side channel attack. More precisely, is it possible to recover the private key through power consumption side channel attack on the decapsulation algorithm? So before to talk about the attack, I will give a partial description of classic Mac-Leese as it is required to understand the attack. So first, the key generation algorithm. So it takes as input 3 parameters, M, N, and T, and that I will detail later on. And it will output a private key and a public key. It begins by generating an random ordered subset of n elements alpha of f of 2 to the power of m. That subset is called the permuted support. And then it will generate a Gopa polynomial g of degree t, and which coefficient are in f of 2 to the power of m. And then it will exploit G and L to compute a binary parity check matrix, HPub, which is the concatenation of the identity matrix and matrix T. And finally, it will return the private key, which is equal to G and L, and the public key, which is equal to T. So now for the decapsulation algorithm, it takes as input a ciphertext CT and a private key, and it will output a session key K. So it starts by padding CT with zeros to get a new vector V. Then it will compute a parity check matrix HG2. So that is computed using G and the alpha of L. And what is important about that matrix is that each column is correspond to the successive powers of one particular alpha multiplied by g to the power minus 2 of alpha, and the order of the alpha in HG2 is the same order as the permitted support. And then it will compute a syndrome S as a product of HG2 time V transpose. So that's all I will describe for the decapsulation algorithm, as the rest of the algorithm is not required to understand the attack. So now for the security parameters, as I said, there are 3. So M, which is the field extension degree, N, which is the number of elements of the permitted support, and T, which is the degree of G. So there are different Michaelis sets of value that have been submitted to the NIST, and they offer trade-off between security and performance. And there is also a set of values called the Toyelis set that is used for research purpose only. So now that we are that's all we need to know for now about classic Michaelis. So let's talk about the attack. We started with the assumption that there was a power consumption side channel leakage on the Hamming weight value of the coefficient of the HG2 matrix during the syndrome computation. So based on that assumption, we designed the following 4 steps attack that takes as input a side channel trace of the execution of the classic Michaelis decapsulation, and that starts by estimate the Hamming weight of the coefficient of HG2. Then it will exploit those Hamming weights to recover N of pairs alpha G of alpha. So I will explain later on what I mean precisely by N of, but for now we will say that this is equal to M times T, which is approximately equals to N over 4. So it is important to notice that at this step we do not need to recover the N pairs alpha G of alpha. Then we will exploit T pairs among the recovered one to recover G. And finally, we will recover L. So one of the main features of our attack is that it requires only one attack trace with no control over the ciphertext. So for the targets, we used an STM32 microcontroller and a Chip Whisperer Pro for power consumption measurements. And we used the reference implementation of the syndrome computation that was submitted to the NIST post-quantum standardization process that computes the syndrome using 2 nested loops. So the first loop will iterate over the column of HG2, and it starts by computing the first coefficient, so G to the power minus 2 of alpha, and then the second row, the inner one, will iterate over the rows of HG2, and first it partially computes the syndrome, and then it will multiply the coefficient of HG2 by alpha to get the following coefficients. So although this is not the usual way to compute a matrix vector product, it is done that way to reduce the required number of computation. And so before to perform the attack, we performed a leakage assessment to assess our hypothesis. And so we used the ANOVA test. And we saw that, as we expected, the Hamming weight value of the coefficient of HG2 leaked during the syndrome computation. So now that our hypothesis was confirmed, we performed the attack, and we started with another hypothesis, which was that the Hamming weights leakage could be modeled as Gaussian distributions. So with one Gaussian distribution corresponding to one possible value for the Hamming weights. So based on that, we performed the template attack, so which is a profile side channel attack that works in two phases. So during the first phase, the training phase, we used a replica of the device that we want to attack, on which we run many random known values, on which we run the syndrome computation using many random known values for the private key, so that we could exploit the power consumption traces recorded to estimate all the parameters for the Gaussian distributions. And then in the second phase, the attack phase, we used those Gaussian distributions to actually recover the Hamming weights of the Hamming weights value of the coefficient of HG2 using the power consumption traces of the syndrome computation with the using the unknown private key. So here we can see the Gaussian distribution that we observed, that we obtained experimentally for m equals to 9, and we can see that every Gaussian distribution are slightly overlapping with each other. And this is something that we observed for all the value of m. So that explains why all our classifiers have an accuracy slightly lower than 100%. However, for all our classifiers, the accuracy was higher than at least 96%, and so that was enough in practice for our attack to work. So we can now go to the second step. During that step, we will gather the Hamming weight into a list that correspond to the column of HG2, and in parallel, we will, as we know that alpha and g to the power minus 2 of alpha are in are elements of f of 2 to the power of m, we can pre-compute a cuboid that will contain all the possible list of Hamming weight that we can recover. And then the idea will be to compare the recovered lists with all the list of the cuboid until we find the corresponding one. And so we can recover the corresponding alpha and g to the power minus 2 of alpha. So in practice, there are three possible outcomes when performing that step. So the first one is when no pair matches the Hamming weight list. It means that at least one of the recovered Hamming weight was wrong, and so we discard that list. Then another possibility is the multiple pair outcome, where several pairs will match the Hamming weight list, We will see in the next slide how often this outcome can happen. And in such case, as we have no way to distinguish which pair is the correct one, we will also discard that list of Hamming weight. And finally, the outcome we are the outcome that we need for our attack, the unique pair outcome, where only one pair matches the Hamming weight list. And in such case, we store that pair for later use, to use later in our attack. So concerning the multiple pairs output, we computed the cuboid for all the value of m, and we also computed the ratio between the number of unique lists and the number of and the total number of lists of Hamming weight in the cuboid, and we saw that the unicity ratio was always higher than 99% for all the value of m. So here again, this means that that was high enough, that unicity ratio was high enough for our attack to work, and so we can go on to we can continue to the next step. But before that, we made two improvements in that step. First, we reduce the Hamming weight list. We realized that it was possible to reduce the Hamming weight list while preserving the unicity ratio. And then we used a hash table to speed up the recovery of the pair alpha G of alpha. So now that we've recovered our pairs, we select T pairs among them to recover the Gopa polynomial G through an interpolation. So now we have recovered the G, and we can go on to the last step, which is about the recovery of L. But before to explain that step, I must get back to the public key generation inside the key generation algorithm, as it is required to understand that step. So the public key generation is made by computing a matrix H using G and the elements alpha of L. So here again, what we can see is that each column of H corresponds to the successive power of one particular alpha, and the order of the alpha in H is the same as the order of the order in L. And so once that H is computed, it is transformed into a binary matrix H prime by mapping every coefficient of H, which are elements of f of 2 to the power of m, into m binary elements. And so we get the binary matrix H prime. Then we will multiply H prime with a matrix S during the Gaussian elimination step to compute the H-pub matrix that I described earlier. So now that I explained the public key generation, I can explain how to recover L. So we use H-pub G and the alpha that we recovered to recover L. So first, we will compute a submatrix of H. In fact, we will compute the column of H that correspond to the alpha that we recovered. Then we will expand that submatrix into a binary submatrix of H prime. And that binary submatrix will allow us to recover S. We will use the inverse of that binary submatrix and a submatrix of H-pub to recover S. And once we have the matrix S, we will be able to revert the Gaussian elimination step and to get H prime from H pub by multiplying H pub with the inverse of S. Then we can compute H from H prime, and finally we can recover the full support, the full permitted support, by dividing the second row of H by its first row. So now that I explained the attack, I can explain what I meant earlier when I said n of alpha. If we want, as I said, if we want to recover L, we must first recover the matrix S that is used in the Gaussian elimination step, and this is an empty times empty invertible matrix. And to do so, we must find an invertible submatrix of H prime, which means that we must find empty linearly m times t linearly independent columns of H prime. And so if we only recover mt alpha, the probability that the columns, that the corresponding columns are effectively linearly independent is actually less than 30%. So to increase the probability to have empty linearly independent column, we must take in practice, we took in practice MT plus 10 pairs, so that this probability was equal to 99.9%. So now for the success rate, we can see that the success rate is equals to 100% for all the Michaelis sets of parameters, as long as the accuracy is higher than 94.5%. And an interesting result to see is that when the value of the security parameters is higher, then the accuracy required for the attack to work is lower. So now, for the comparison with the previous power-based key recovery side channel attack on the classic Michaelis scheme, what makes my attack better than the previous one was that we worked on the decapsulation algorithm, which compared to the key generation, which is used more often than the key generation algorithm, so that makes him more vulnerable. Then we required only one attack trace with no control over the ciphertext, and finally it is a full key recovery. So to conclude, I presented a new full key recovery attack that works in a cubic time and that requires only a single attack trace with no control over the ciphertext, and that does not require perfect accuracy. And the source code of our attack is available on our GitLab repository. And concerning the future works, so first, attack improvements could be made by, for example, reducing the classifier required accuracy, or exploiting G in the recovery of alpha G of alpha. Sorry. So changing the side channel attack, or another interesting aspect could be to find countermeasures to the attack. So, all right, that concludes my presentation. Thank you for your attention. And do you have any questions?
Thank you for the very nice talk. Do you have any questions? Maybe one quick question, because we're almost out of time. Okay, then, there's one, yeah.
Hi, thank you for your nice talk. There is a result by Kishinova and May breaking copper-based Michaelis fins, which may be able to help you and improve and even work with a few number of alphas. I think they only need Tm minus 2t plus 1. So maybe, I don't know, do you know about this result? Or have you considered this? Is there some reason why you can't use this to optimize your attack?
Sorry, which article are you talking about?
The paper Breaking Gopper-Based Michaelis Defense by Kirscher, Nova, and May. I don't know. Maybe you don't know about this paper.
Yes.
Oh, okay.
If I remember correctly, so I'm not totally sure, but if I remember correctly, we did not use it because I guess the complexity is slightly higher than what we do. I'm not sure, but I think that was the reason why.
Okay, so with similar amount of data, your attack just works in linear time, maybe, and they require longer time or something. Maybe we can talk about this.
Yeah,
it sounds interesting. Thank you.
Thank you.
Okay, then let's thank the speaker again and all the other speakers of the session.